Hello, everyone. I'm Keith DeStone with the Harvard University Center for Hellenic Studies, and I would like to welcome you back to the Cosmos Society online open house series, a venue that's meant to bring current researchers into conversation with the broader CHS community. Our guest today is Dr. Graeme Bird, who is a native of New Zealand and who has been teaching for more than 20 years at Gordon College north of Boston, where he is professor of linguistics and of classics. His interests include Greek mathematics, computer programming, jazz improvisation, early English literature, as well as Greek and Latin language and literature, and Indo-European linguistics. He teaches mathematics, including Greek mathematics, which is our subject today, as a lecturer at the Harvard Extension School and the Summer School as well. And he's a member of the CHS-affiliated Homer Multitext Project. And he's a piano player, both professionally and for fun, as I understand. So Graeme, thanks for joining us today. I'd like to turn things over to you and ask you to begin, if you don't mind, by sharing with us what first sparked your interest in the ancient world. So, thank you.
Thank you, Keith. Thank you all very much for having me. And I was just thinking about this. When I was a young teenager, I found my father's high school Latin textbook. And I thought this was the most wonderful thing. And I couldn't wait to take Latin, which I did in high school in New Zealand. I went to a boys' high school. And so that got me into Latin. And then after 3 years of Latin, we got a new Latin teacher. And he walked in one day. There were 5 of us, I think, in the class. This was, I guess, 11th grade. And he said, "Boys, would any of you like to learn Greek?" And we all put our hands up right away. And so that got me into Greek. And there wasn't a class scheduled for us. So we sat outside under a tree and learned Greek for the first few months, which just is delightfully pastoral. And so those are my 2 main memories of getting into Latin and Greek. And then I went to Auckland University and majored in classics. And it's sort of been one of my main passions ever since. So it's the people that we're influenced by, isn't it? In my case, my father and a really inspiring teacher. So that's how I've got my start.
Yeah, you're so right about the teachers, the influencers. Thank you. Thanks, Graeme, for sharing that.
Yeah.
All right, take it away.
Okay, so can I see my slides? And then will I be able to advance them?
You may have to start sharing them again.
Share them again, okay.
Yeah.
And by the way,
process.
Can I make them available? Can I email them to you, Keith, after the session?
Yeah, sure, definitely.
So can you see them now?
Yeah, perfect.
Okay.
You can see your title slide there.
Okay, so Euclid Saves Us from Ignorance. Okay, here we go. So I sent you, I think, a 12-page handout. Hopefully it wasn't too much, but this was from Proclus, who apparently was born in Constantinople, studied in Alexandria, and then went to Athens and became a sort of successor to Plato in the academy. This is hundreds of years later, of course. But the one of the things I sent to you was, this is the last paragraph of Proclus's opinion of Euclid. And I got my title for today's talk from the last sentence. So let me just read that. "If you seek to add or subtract anything, are you not unwittingly cast adrift from science and carried away toward falsehood and ignorance?" So I thought my title is Euclid Will Save Us from Ignorance, as long as we don't add or subtract anything. So I think you can tell Proclus had a slight bias, which is pretty clear here. I think he was a big fan. So I have spent a lot of time in Homer, Iliad, and Odyssey, as I'm sure many of you have. So this is the beginning of Homer's Iliad, Menon Aida Thea. And tell me if I've made any mistakes in my Greek. I try to be really careful, but I'm always, we're all human, right? So the beginning of the Iliad, sing goddess of the wrath, and then it's obviously the wrath of Achilles. And then beginning of the Odyssey, Andra mai enapamusa, tell me muse of the man, which is going to be 20 or 30 lines later, we'll find out who it is. And then here's the beginning of Euclid. Semeon esten hu meros uthen. A point is that of which there is no part. And I'm kind of juxtaposing it. Sometimes I joke with my students, this is the very beginning of Euclid's Elements. Doesn't it just sound like sheer epic poetry? And then we laugh because it's not exactly like Homer, but you've got to start somewhere. The Iliad starts with the wrath, the Odyssey starts with the man, and Euclid starts with the point, which seems pretty sensible for a book on geometry. So whenever the translation has bits in parentheses, those are not in the Greek, but necessary to make sense, because as you know, Greek is a little bit more concise than English. So this next slide, I have to apologize. I've stretched it out a bit because I changed my slide format from, this one to this one, and it stretched out the painting. I just realized that today. So, but anyway, this is from within the Vatican in Italy. And this is this famous painting by Raphael, just amazing. I'm sure some of you have been there. It's probably one of the most popular things there, and it's always full of tourists, so you kind of have to wait for them to go away before you can get a really good look. But many of these have been identified, but I talk about two of them in my Greek math course. So on the left here, you've got Pythagoras and his chalkboard. And it's possible to zoom in and see what's on his chalkboard, and it's very easy to read. And I actually wrote a tiny article about his chalkboard and a mistake on it made by Raphael, who didn't know Greek. But anyway, we won't do that today. Let's do, on the right, we have Euclid and his chalkboard. The trouble with Euclid's chalkboard is it's at such an angle, it's almost impossible to see what's on it. So let me just, advancing a slide here. So there's Euclid with his pair of compasses. And I'm always very particular to call this a pair of compasses, not a compass, for obvious reasons. And there he's being surrounded by some young folks who are amazed. And he's drawing something on this chalkboard. And if we zoom in even further, it's really hard. And people have written articles about what it is, because whenever there's uncertainty, there's room for discussion. It's some kind of six-sided thing, one triangle overlaid on another. But I'm not going to get into that because you can tell this is pretty hard to read. But anyway, Euclid, along with Pythagoras, and as you probably know, Plato and Aristotle are some of the key figures in this marvelous fresco in the Vatican. So I sent you some definitions. Well, we've just looked at definition 1. I sent you a whole lot of definitions. This is one of my favorites. I don't know how much mathematics any of you have done. I teach various classes, and some of them are full of people who are afraid of math or maths, and I try to soothe their anxiety. But if you remember from whenever you studied geometry, the definition of a circle, I bet it's nothing like this. So let me read the English here. This is definition 15. A circle is a plane figure contained by a single line, which is called a circumference, such that all of the straight lines radiating towards a circumference from a single point lying inside the figure are equal to one another. And when we read this in class, we have a bit of a chuckle because it seems very counterintuitive. The bits in square brackets, these are actually considered to be interpolations in various Greek manuscripts, meaning they are in some manuscripts, but the editors think they shouldn't be there because you don't need them. So that's up for debate. But let me just read this in Greek, because I'm sure many of you love reading things in Greek. Kuklos estis schema epipedon hupa mias grames periechomenon, and I'll do this bit, he kaletai peripheria pros hen aphenos semeu ton entos tu schematos kemenon passai hai prospiptusai euthei prostain tu kuklu peripherean isai alelas esen. It's a mouthful, but the peripheria, this is the circumference, which is cognate with the Latin circum periferens ferea. So there's a lot of cognates in the language between Greek and Latin. But anyway, I'm showing this just because it's fun to read, and we'll use it in a little bit. I also sent you postulates, atemata. There's 5 of those, and here's one of them. Atesto apopantos se meu epipan se meon euthean gramen agagain. Let it be postulated to draw or to lead a straight line from any point to any point. And then I've added in my comment, this actually should be in parentheses. This means that Euclid says you're allowed to use a straight edge or an unmarked ruler, because famously Euclid allows you to use 2 things, one of which is an unmarked straight edge. Then the second postulate, kai panti kentro kai diastemati kuklon graphistai. And it's also postulated to draw a circle with any center and radius. And then my comment, thus a pair of implied collapsible compasses is allowed. So when you do your compasses, as soon as you lift them up, they're supposed to collapse, and that's part of the system. He's trying to keep it as simple as possible, and on this simple basis, with 2 simple tools, to build an amazing structure of the elements of geometry, which is still published today, one of the most published books ever. Okay, some common notions, and koinai enoi tato auto isa kai alelois esten isa. Things equal to the same thing are also equal to each other. So I have my students write this as some equations. People in Euclid's time didn't have equations, and they didn't use generally letters for numbers quite like this. So this is a sort of a modern version. So things equal to the same thing. Here's thing 1, A, and here's thing 2, B, and they're both equal to the same thing, C. So that means thing 1 is equal to thing 2. Just think Dr. Seuss. Anyway, and then another common notion, kai ean isois isa prostethe. Look at that lovely aorist passive subjunctive. Ta hola esten isa. And if equal things are added to equal things, the wholes are equal. So you've got, here's 2 equal things, A and B. Here's 2 other equal things, C and D. And if you add one of the equals to that and the other one to that, A plus C is equal to B plus D. These really are common. I mean, if you plug in numbers, you'll be able to see that these are common notions. But because it's Euclid and he's trying to start with a small collection of definitions and axioms and then build everything on it, he tries to leave nothing to intuition or guesswork. The famous, I didn't give this one to you in Greek, this is the famous or infamous parallel postulate that those of you that have done non-Euclidean geometry will know, that if you ignore the parallel postulate, you can come up with non-Euclidean geometry like curved space, Einsteinian relativity, all of this wonderful stuff that we definitely won't do today. But I'm showing this partly because if you take 2 lines and you produce them to infinity, ep apeiron, boundless or limitless, and I think I sent this to you on the reading. What does it mean to be produced to infinity? So, and by the way, apeiros is synonymous with Latin infinitus, both meaning not limited, not bounded. And also, just by the way, I was reading a book review of a new book about Anaximander, one of the very earliest Greek philosophers, and his theory of the apeiron, of the unlimited, as the first principle of nature. So I think I'm going to buy this. It's under $20. I think I can do it. But this is the thing that I sent you to look at. So this is using limitless outside Euclid. So a fragment of Pindar has limitless. Anyone? Skotos? Feel free to jump in. What's Skotos?
Darkness.
Darkness, yeah. So I haven't actually looked at this fragment, but apparently it talks about limitless darkness. And then in Herodotus, he talks about Plathos being limitless, and then Plato in the Parmenides talks about arithmos, a number that is limitless in magnitude. And then Plato's laws. Anyone want to give a shot at this one? What's going on here? What's limitless here?
To increase injustice to the unlimited extent.
Yeah, that sounds pretty bad, right? Yes. Now, I'm trying to see who that was that said that.
It's Jack.
Jack, thank you, Jack. I can see some people, but not everyone at the same time. So Plato talks about, increasing injustice without limit. So that sounds bad. And then this is an inscription from one of the databases, Chronos, so limitless time. And then this is Aristotle talking about Anaximander and his principle of the infinite, the unlimited. And then Aeschylus is Agamemnon. So spoiler alert if you haven't read it. Agamemnon is about to die, or already has died, thanks to his lovely wife, Clytemnestra, and he's wound up in these tapestries / garments, and amphiblaistron, something wound around him with no end. He can't escape. So it's just fascinating to see a word that's used technically in Euclid and how it's used in a non-mathematical way. So I'm sure we're all lovers of words as far as possible. A quick note on the Greek number system. So you all know there is 24 letters in the regular Greek alphabet, but one of the Greek number systems, I'm calling it the second, there's another number system. If you need 9 letters for the units, 9 for the tens, and 9 for the hundreds, you really needed 27 letters. And so there were 3 letters brought back just for mathematics. And so here they are. These are screenshots taken out of Sir Thomas Heath's book called History of Greek Mathematics, Volume 1. I mentioned that at the very end just as a reference. But you'll notice that this zeta is the 6th letter, but zeta is used for 7. And so this letter, there used to be a digamma if you go back far enough. Later on, it became called stigma because it's a combination of a sigma and a tau. And so this is used in mathematical texts for a 6. Then we go over to the tens, and you'll recognize this as a non-traditional Greek letter, koppa with a Q. When the Greeks got their alphabet from the Phoenicians had 2 different kinds of k sound, a regular velar kappa, and then a further back uvula, which is still in modern Arabic, but not spoken in modern Hebrew. So koppa was brought back just for 90. And then this one called Sampi was brought back for 900. It's some kind of sibilant, some kind of hissing sound that the Greeks didn't need, but they brought it back just for the math. And I prefer this shape because this T looks too much like this T. And I actually gave an online math quiz number 1 to my math in the Greeks class on Canvas this week, and I need to go and grade it. And one of the questions had I can't remember. It had either one of these or one of these. We'll see. I'll see if they got it right. These are the lowercase Greek letters being used for numbers. And they often had a little line over them, but Heath says it's too difficult for the printer, so I'll skip putting the line over them. When you get up to thousands, you use an alpha with a dash before it for 1,000, 1,000, 2,000, 3,000. So anyway, that's just a heads up about the Greek number system, one of the Greek number systems. Now, we're going to look at a proposition today. We're looking at Euclid's very first proposition. And as we'll see, one of the important components of a proposition is proving that whatever you said or did, that you actually prove that it's correct. And there's two kinds of types of proofs. If you're trying to prove that you said something true, you end up by saying "hoper ede dexai," which is actually, I shouldn't put that in parentheses anyway, which is the very thing it was required to show, dexai from deiknumi. We're all familiar probably with Latin QED, quod erat demonstrandum, the thing which was to be shown. But in Greek, it's hoper ede dexai. So that's if you're trying to prove that you're saying something and you're saying it right. If you're trying to draw something, as we're going to in a minute, if you're attempting to construct something, you would end by saying hoper ede poiesai, which is the very thing that it was required to do or make or construct. And so that would be in Latin less commonly known QEF, quod erat faciendum, the thing that was to be done. So Euclid is very particular about proving things because if you remember what Proclus said, it's all about rigor and proofs and having everything in the right order and only using things that you've already proved. So it's a great demonstration of how to be logical and rigorous and all of that, everything in sequence, which to me makes it delightfully different from reading Homer's Iliad, right? I mean, things are in order in Homer's Iliad, but of course we have, and in the Odyssey we have flashbacks, and we pick up themes, and we finish one scene and we go, meanwhile, back in Ithaca, this was happening. You don't have anything, you don't have anything quite like that in Euclid, but it's a very different kind of purpose. Okay, parts of a proposition, and here's a reference to Heath, Volume 1 again. By the way, Heath wrote his books in the 1920s, and as you're aware, things have changed since the 1920s. So when you pick up Heath's book, he assumes that everyone is a schoolboy and knows Greek. And Janet, you'd agree times have changed, right? Yeah,
I'll step in and agree for sure.
You what?
I'll step in and agree for sure. Things have changed.
Yeah. So I like to have fun with my students, as you can probably tell. I can't talk for long with a straight face. And so when he talks about schoolboys, we sort of mock him gently. And when he gives Greek words without any English transliteration, I ask my class, I don't ask them to learn Greek. I ask them to learn the Greek alphabet. Well, I don't ask them, I order them actually, because I want them to be able to pronounce any Greek word they see in the book, which is not too much to ask, right? I'm sure all or most of you read some Greek, and I figured asking them to say protasis is not too difficult. So, and when I tell them to transliterate, I would tell them to ignore the accent. So just say, protasis. So this takes about a week just to get the alphabet under their belt, so to speak, protasis. And then we could talk about the grammatical use of the word protasis, but I don't usually. And then I tell them not to ignore the breathing marks. So don't ignore the comma, but do ignore the accent, which is quite interesting since they're so close together. So I would want them to write, ekthesis, and then diorismos, and then kataskoe, and then include knowing that the smooth breathing means no H, apodexis, and sumperasma. So propositions in Euclid can have up to 6 components. In some components they have to have an enunciation. It's like, tell us what you're trying to do. They have to have a proof, and they have to have a conclusion. And the conclusion is usually just repeating what they said they were going to do. Well, what he said he was going to do. You only need a construction if you need to draw something, but you don't always need to draw something. So anyway, let's take a look here. Proposition 1.1. I think I sent this to you in multiple forms, Greek and English. So so here we go. Epites dotheses ertheas peperas menes trigonon isopleron sustesastai. And interesting, he uses the definite article here. He doesn't say on a given straight line. He says on the given finite. So here, a perfect passive participle, having been bounded, having been limited. And here's the word for straight without the word for line. So this word straight from now on is pretty much going to mean straight line. And then an aorist passive participle here. So there's lots of rich grammar here, except I don't require grammar in my regular class. Trigonon should look really familiar. So that's a triangle. Isopleron is it matches exactly with equilateral. Iso, equi, pleuron, lateral. And we talk about the etymology of pleurisy and things that are related to pleuron, sort of part of the anatomy around the lungs. And then sustesastai, an aorist infinitive, to set up. So there's no, it's an implication of, well, there's some finite verb not expressed. So to do this, here's how to do this. So this would be the enunciation or the protasis. And so this is kind of famous because it's the very first one. And you might be thinking, oh, what's so special about equilateral triangles? And it turns out that following Euclid's principle of only using things that you've already used or proved, it turns out that equilateral triangles are really, really useful and necessary for doing other things like bisecting angles, bisecting lines, those two things in particular. So he does this first, and as you'll see, it's really, really easy to do, and then he'll use it in later propositions. So let's see. So I think I sent you this, maybe. This is from this free online Euclid. How about that? 1,000 pages, or depending on the layout, 500 or 1,000 pages of Euclid, either side by side, Greek and English, or on alternate pages. So Keith, how often do people do all this work and put it online and make it free to all of us? It happens, does it?
Well, it does happen quite a bit more and more these days, actually, thankfully.
Well, actually, CHS is a model for that, isn't it?
Yeah. We have 1 million, not literally 1 million, a lot of books online.
Yes.
Just waiting for you all to read.
Yes. Yeah. And I remember being, I remember being fortunate enough to go to Venice with Greg Nage and a team back in 2007, was it? And we had some professional photographers digitizing the wonderful manuscript of the Iliad Venatus A. And that's all freely available online now in high resolution images. And incredible amount of work's been done on that. So I think it's wonderful, the generosity of spirit and all of that kind of thing, because you don't always find that in academia, as you know. So whenever I look at this, I think MasterCard. So I ran that by my class, and then of course they did some instant Google research and found that yes, there probably is a link somewhere that whoever came up with the MasterCard logo maybe was thinking of Euclid Proposition 1.1, and also the shape, the dimensions of a MasterCard or Visa or license or ID are somewhat close to what's called a golden rectangle, but that's for another day. So anyway, here's the Greek that I just read, and here's a translation slightly different from mine. So this would be the setting out. I mean the enunciation. Here's what I want to do. Just make sure I say my terms in the right order. I'm just going back to my the 6 parts of a proposition. Where did I put them? Yeah, here we go. This would be the setting out, meaning you said you're going to do it on a given straight line. Well, where's the given straight line? Well, it's AB, or alpha beta, and it's finite. When Euclid says line, he means finite straight line. When modern math people say line, they mean infinite line. So there's some differences. So here's AB, or alpha beta. This is our starting point. And this diagram actually is the finished product. So we don't get it in stages. So anyway, so this was the ekthesis, and then here is the definition, or the diarismos. So it is required to construct an equilateral triangle on the straight line AB, or alpha beta. Now here's the finished product, but let's pretend we haven't done it yet. I actually I do this in class on a whiteboard with a giant pair of compasses, and I have to practice because I don't want the things to collapse halfway through a circle, because that would give you a spiral, which I don't want to do. And then my students, for their assignments, have to do this by hand. Strictly no software allowed. So we need to see their actual pencil marks, which they scan and upload. So we're trying to do it in the spirit of Euclid. And it's kind of fun. It's kind of fun, actually. So where do we go? Now, this looks like quite a lot, but what I want you to look at is the underlines. So I'm going to read this, and then we'll stop at the underlines. Let the circle BCD with center A and radius AB have been drawn. Postulate 3. Now, I'll go back to the previous slide in a minute so we can see the circle. Does anyone remember postulate 3?
Yeah, postulate 3 was you could draw a circle with any given radius.
That's right. Any center and radius. That's it. So this postulate 3 is put in by a commentator. I don't believe it's usually in the manuscripts, but this is just showing that Euclid is doing something that he said you're allowed to do. So Carl, yes, right on. And then again, the circle, another circle with a different center and radius, postulate 3 again. And then let me just finish this paragraph. Let the straight lines CA and CB have been joined, blah, blah, blah. We'll get back to the footnote in a minute. Let them be joined to the point C, where the points A and B, to the points A and B. Postulate 1. Well, Cara, while I have you there, what was postulate 1?
Basically, you could connect at any 2 points with a straight line.
That's it. That's it. So that's the ruler. So this says we're allowed to use compasses. This says we're allowed to use a ruler. So let me just go back. So starting with AB, we drew a circle with the center A and the radius AB. And I do this in front of students, and sometimes it is a disaster, but last week it worked out. And then I do this circle around here. And this D is just a point to label a circle. And then you pick your second circle, point B and radius BA, and you do your circle around here. and then they intersect at point C. And so you use postulate 1 to say, I'm allowed to join any 2 points, A and C and B and C, because I'm allowed to use a straight edge. And then it looks like we've drawn an equilateral triangle, right? But looking like is not good enough because diagrams can be deceiving. So anyway, this was our first paragraph. Let me go ahead. So this would be the catascue, the construction. Now comes the 5th step, which was the sumperasma, the proof. No, I'm sorry, wrong word. Apodoxis, sorry. And the proof looks like it's the longest part of this proposition. And since the point A is the center of one circle, and he talks about definition 115, this was the definition of a circle. Remember that Weil definition with all of these lines radiating out and blah, 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 and they're all the same length, namely their radii. So I'll go back to the diagram in a minute, but point A is the center of one circle. AC is equal to AB. Well, let me go back now. A is the center of the left-hand circle. AC and AB are equal because they're radii. They radiate from the center and they're all the same length. Similarly, point B is the center of this circle and it has 2 radii, BC and BA. So they're the same length. So we've got AC is equal to AB and we've got BC is equal to BA, and BA is the same as AB. So now whenever Euclid says but, you know he's getting to something exciting. He's picking up something that we already knew. CA, okay, so I'm going to go to the next slide, which has a picture that'll be easier to read. But before I get there, CN1, what's CN1? Not to be confused with CNN.
That's the transitive property.
Yes, or common notion 1, go. Yes, exactly right. Things equal to the same thing are equal to each other. And so thus, blah, blah, blah. So we'll look at this on the next slide. All these 3 lines are equal. And so then here's the sumperasma, the, how did I translate that one? The conclusion, the triumphant conclusion. The triangle that we just drew is equilateral, and it was constructed on that line that I said I would do. And then you can just hear him saying, yes, I did it. So this would be hoper ede poiesai, the thing that I was required to do or make. So back in the COVID days, I did this on a virtual whiteboard from my office, and it took a lot of practice to do this on a virtual whiteboard. So AB is equal to AC because they're radii of the left-hand circle. AB is equal to BC because they're radii of the second circle. Common notion 1 says things that are equal to the same thing. What is the same thing in this case? It's this AB. This one's equal to this one's equal to this, so this must be equal to this. So AC is equal to BC. So we have 3 equal line segments making a triangle, and the very definition of an equilateral triangle is a triangle with 3 equal sides. QED in Latin, but of course we don't say QED, we say hoper ede poiesai. I guess OEP, but I never say that. Now, if you've read the history of this, just going back to this, the footnote. I love these little dagger footnotes up here. Where the circles cut one another. Footnote. And there's hundreds of pages of ink have been spilled on where the circles cut one another. So next slide. The assumption that the circles do indeed, cut one another should be counted as an additional postulate. I'm just going to do this first sentence. So it sounds like Proclus told us if you try to add or subtract anything from Euclid, you'll be cast adrift into the seas of ignorance. But the implication here is Euclid left something out. Uh-oh. Now, we know when you draw two circles and they cross, it kind of is obvious they meet at a point, right? I mean, Jack, isn't it obvious?
Yes.
But how do you define obvious? Yeah, obvious is a slippery word, right? It just feels obvious to me, but apparently soon after Euclid wrote his Elements, people complained and said, you never proved that if circles, just because one goes over another one doesn't mean they actually cut at a point. You assume something because you were misled by a diagram, which is a real slap in the face for Euclid. So I remember taking a course years ago called Non-Euclidean Geometry, and they tried to fix Euclid, which sounds very arrogant. But anyway, they came up with another postulate, which mean something like, I think it was the betweenness axiom. Between any 2 points, there is another point, which sounds like continuity in the modern math sense. So anyway, some people say this is embarrassing. I still love Euclid, so, you know, we're all human kind of thing, right? But how about this, for those of you that love grammar? You might have been wondering, why does he say, let the circle have been drawn? Oh, I forgot to thicken the auxiliary. Those of you that have studied Greek, how often have you seen the form gegraphtho? Jack.
They haven't been drawn or written.
Yeah, let it. Sarah, how about you? Do you use gegraphtho a lot in your everyday life?
Oh, all the time. No, I haven't seen this form before, although I could recognize what it was, but yeah.
Yes, yeah, good. Yeah. I mean, how often do you need to say, let something have been done? I mean, it sounds vaguely, I think it's glorious. I think if you look in the in the lexicon, it'll probably say, you know, Euclid. It'll say Euclid used it, and maybe no one else, because why would they? So let it be. We would be happy with let it be drawn, but let it have been drawn is like it was there all along, kind of thing. So maybe he's getting Platonic, and there's this, you know, the world is full of perfect circles, and we're just going to use one. It's already there, and we'll just plonk it down, or whatever. There's all kinds of interesting ramifications, but it's
related to the laying the predicate for what he's doing next, and being absolutely clear that this has been done as a step for the next thing, right?
I guess so, yeah. But it's kind of like we're not doing it now. It's like been there all along, or it's been there anyway since anyway, whatever. It's really good to think about.
But it's in that third person imperative, you know, like the esto.
Yeah, exactly. There's a lot of those. Yeah. No, and here's another third person plural passive imperative. Epedzeuchthosan, let the straight lines, let them be joined. So gamma alpha, gamma beta. So there's wonderful Greek grammar. It's things that you'll never see anywhere else. So Maria, is this used in modern Greek, would you say?
Well, no.
These?
I only know that because I know ancient Greek Attic grammar very well. But this grammatical type, it's the first time that I see that being used. Yeah,
and yeah. Thank you. So it's a very narrow, specialized use. So we shouldn't be surprised. But anyway, and we know very little about Euclid as a person. So when you read Euclid in Greek, you'll see lots of third person verbs, and you'll see lego a lot. The only time I think you see a first person is I say, meaning I claim that da 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 da. And then I think you will hardly ever see a second person verb. I think there are a few, but Euclid's not really, he's not having dialogues. So the style of Euclidean Greek is it's a subset of classical Greek, but it's only using just what he needs. So I find it really, really, really fun to use and to read. So that's the verb. Now, do any of you like ancient manuscripts? Of course, we all do, right? Why wouldn't we? So, also in the Vatican, I've never been allowed into the Vatican Library because I think you need special permission. But apparently in 1808, it was discovered in the Vatican Library, this 1,000-year-old manuscript of Euclid's Elements, discovered by a Frenchman. And at that time, Napoleon was collecting manuscripts. So luckily, this one got to stay in the Vatican and not end up back in Paris. So there's all kinds of interesting history there. So a copy of Euclid, carefully written by hand in the 10th century, contains all 13 books of the Elements, as well as some commentary and some other things. Euclid also wrote on music, and I've started to read some of his stuff on music, and since I'm a musician, I haven't got very far yet, but it starts with something like, if there were no movement, there would be no sound. You know, if something's not moving and banging against something, you wouldn't have any sound. So that sounds pretty sensible to me. But those of you that know Greek, and even if you don't, maybe this will make you want to learn Greek. And this is available online. I forget the, I can send the website, but Keith, I can't see the very top because it's blocked. Can you?
I can't see anything above.
I see
the line that has Protasis.
Well, you can see Protasis. Okay, I can't even see that. Oh, now I can. I just had to move this toolbar.
We can see all these terms that you mentioned in your first slide.
Oh, good. Now, so you can see Protasis, and notice it has the acute accent there. And this is in capitals, which are much easier to read. And it has the what we call lunate sigma for both sigmas. So it has Protasis with a little punctuation mark. And then it gets harder to read, right? Maria, since you know Greek very well, how is this for you to read? Oh, you're muted, Maria.
Which part do you want me to read?
So can you see my pointer?
Yes.
So this can you make?
Well, this is ep.
Epi.
Yeah, this is epi with the
Epi.
yes.
Well.
Yeah, this is an eta, so tes.
Tis.
Or tes, yeah. And then this is,
or
yeah, this is a delta omicron theta, and this is epsilon iota together, sigma eta sigma.
Tis.
So in classical dothesis or dothesis, yeah. And then these things here, this is a combination epsilon iota. This is epsilon upsilon. And then let me here's an easier one. What's this word?
This is trigonon. Definitely.
Yes, and notice the nu is not what we're used to in printed Greek text, right? It looks like a backwards mu, but this is a nu. And yeah, the omega looks like infinity, so to speak. And then here's
Isopleron.
Yeah, and then isoplero, and then the ron goes over to the next line. And then here's this is a sigma tau. So sus tesastai.
Yeah.
So, you know, given a bit of practice, you know, take a few hours, you can really get quite fluent at this. But it's really nice that the scribe put in the subdivisions in capitals, Protasis. And then here's the second one, right? Jack, what's that one?
I don't see your cursor.
Oh, can you see my cursor?
Excesses?
Ecthesis, yeah.
Ecthesis, yeah.
And this little T on its side, this is a smooth breathing and acute combined in one. So these are some of the, I spend a bit of time reading these because I think they're so fascinating. I'd love to spend more, but you know, there's only 24 hours in a day, right, Jack? I wish there were more. So the capitals are easy to read, and then we go to the lowercase, and now all these ligatures make it much more, I like to say, fun, but it slows you down a bit. Now, down here, can you see alpha with a line over it?
Mhm.
And then this letter is actually a beta. So in medieval manuscripts, beta is very often written like this, which looks nothing like the beta that we know and love, right? And the fact that they have lines over them means this is the line alpha beta. So it's using alpha and beta as letters, labels. So all that to say, in your spare time, if you have any, brush up your Greek or learn Greek, and then look at some of these pages of these wonderfully, and you can tell this is professionally written by a person that cares about its subject matter. And I mean, there's X hundred of these propositions to write. So anyone that can stay with this task right through to the end is dedicated. I didn't show you that you can see little traces of commentary in the margin. There's all kinds of scholia at the top, sides, and bottom, and they're a treat in themselves to try and read. But anyway, that was just a taste of the first page of Euclid's Proposition 1.1.
Mhm.
Let's just as we wrap things up. It's 11 o'clock. It's noon, right, Keith? I want to make sure I'm ending at noon. Am I right?
Yeah,
Okay.
just coming up on noon. Yeah.
Yeah.
And if we could have maybe time for a question or two.
Yes.
before that.
I've got a couple of slides just to leave you maybe dazed with admiration for Euclid. So remember Proclus.
Already done. In fact.
So the second to last paragraph, Proclus says, by choice, Euclid was a follower of Plato and connected with the school. In fact, he set up as the goal of the elements as a whole the construction of the so-called Platonic figures, namely tetrahedron, cube, octahedron, dodecahedron, icosahedron. And one of my Euclid has an elegant proof showing that there's only 5 of these possible. It's not possible to have any more than these 5, which is amazing in its simplicity and elegance and sophistication. So this is 4 triangles, 6 squares, 8 triangles, 12 pentagons, and 20 triangles. So just to blow you away, so to speak, the anti-penultimate proposition, which is also my anti-penultimate slide, one of my favorite words, anti-penultimate, eikosaedron sustesasai kai sphaira perilabain, to construct an icosahedron and to enclose it in a sphere. And you're thinking, hang on, all I'm allowed to use is compasses and straight edge. Well, here's part of him constructing an icosahedron inside a sphere. Using compasses and straight edge, drawing something in 3D. I don't know, it just blows my mind, actually. Can anyone see an icosahedron taking shape in there somewhere? I think I see a triangle, S and M. So it's going to end up with 20 of these. Here's another one here. But at this point, I say, I'll just get back to simple squares and triangles, I think. But anyway, this is the third to last proposition in Euclid, and it's kind of mind-blowing. Okay, my actual last slide is, so Maria, I would say Efcharisto, right? I don't know modern Greek, but I know how to pronounce some words. Oh, you know what? I see a typo already. That's embarrassing. Can anyone see my typo on my last Greek word?
You talking about the breathing sign and the circumflex. They don't use those anymore. And plus you don't want an acute on the upsilon. You want an acute on the omega.
Yeah, I got too many accents and they're wrong. So I'm so thankful that I got carried away with a surplus of accents. So I think I got the English right though, right? So thank you. And
Eucharisto, Pili.
Yeah, okay. So let me escape out of this mode. How do I do that? Keith, back to you.
All right, wonderful. Thank you, Graeme. That was amazing. That was even more impressive than the last shape, the 3D shape that you showed us, the icosahedron. That even blew my mind away even more than what had come before. You were right. Well, let me change to the gallery view here, and let's have some questions for our speaker.
Yeah. Oh, Gorgo, yes.
So I was fortunate enough to teach geometry for 5 years when I was much younger in high school. Actually, I taught it to high school students. So this was a real pleasure for me. But my question is that I noticed, for example, there are 3 basic types of triangles: scalene, obtuse, and right. I should say obtuse, acute, and right. And these words have overloaded meanings in English. So I'm curious, 2 things. Do they have the same kind of meaning in the Greek? And also, do they, which was the origin? Did they come from the Greek to, if they do, to the math, or the other way around?
Oh, that's a really good question, Gorgo. Thank you. Yes, so acute is, I'm trying to remember the Greek word, but it means sharp. So that kind of transfers. If someone is acute, they're kind of sharp in a good sense. Obtuse, obviously, if a person is obtuse, that's the negative. You know what? I'm trying to remember the Greek word for obtuse. But you're asking, did it have that other meaning in ancient Greek, right? As well as I think it did. And I would want to find some good quotes talking about a person who's obtuse. That's something. Yeah.
Just or.
So yes, right is orthos. So that and that, yes, as in orthodox and ortho whatever, something that is correct and right and just. So then the mathematical meaning is narrower. Yes. Now, when you said triangles divided into 3, they're also divided
by side.
Isosceles, equilateral, and scalene is another way.
Yeah.
So, which is great. Yeah. Oh, do you miss teaching geometry, Gorgo?
Well, geometry was one of my first loves, that and ancient Greek history. No, I just think it's incredibly beautiful. And the one thing you didn't mention, which I thought you might, is that Plato mentions that no one ignorant of geometry should enter his academy.
Yes.
So it's a way of thinking clearly and precisely. Yes.
That's good. Oh, I wish I put that on. So that's Plato saving us from ignorance, as well as Euclid saving us from ignorance. Yes. And as you know, Plato's works are full of uses of mathematics and geometry to illustrate his points. Yes. Yeah.
Meno. Yeah.
Let me. I see Jackie. I see your hand.
Yeah, I was just wondering when the showing those visuals, especially the last one, when Euclid did the construction proofs for, I guess, as you would say, Plato's figures.
Yeah. Were
they all based on an equilateral triangle? Because that's the basics of his toolbox, was the equilateral triangle. So they all had to be proofed using an equilateral triangle.
Yes. So the idea of a Platonic solid is it's a 3-dimensional solid that has a certain number of identical equilateral, equiangular polygons. So yes, equilateral triangles, squares, which are obviously equilateral, and then pentagons. And when you get up to pentagons, you can't just say equilateral, you also have to say equiangular.
Yeah.
Whereas with triangles, all you need to say is equilateral. So there's all these, you know what I'm talking about, right, Gorgo? I learned geometry from a Welsh geometry teacher, so I still have this Welsh accent in my head of geometry with a Welsh accent, which was just delightful. But yes, equilateral and equiangular, because that makes them more perfect, right, Jackie?
Right, yeah.
So there are some like second tier solids, which I guess you could say semi-Platonic solids, that they have a mix. Maybe they have squares and rectangles, but they're not nearly as good as the real ultimate Platonic.
Yeah. And if those are his first two postulates, did I get the word right? I mean, that's like the golden goal. I mean, you have to go back to the origin, the beginning.
Yeah.
Yeah. In order for it to be real.
That's right. Some of you may, if you've read Plato's Timaeus, one of the last things Plato wrote, he takes the 5 Platonic solids and matches them up with the creation of the cosmos. And so the tetrahedron is fire, and the square is earth, and the octahedron is air, and the icosahedron is water. And then what about the dodecahedron? He kind of has one left. And what does he do with the dodecahedron? He uses it for the construction of the heavens and the universe. Then you think of the 12 signs of the zodiac.
Yeah.
So it's kind of amazing reading how he justifies that the tetrahedron, it's the smallest Platonic solid, so therefore it's the lightest. So it rises like fire, and it's sharp corners, and fire is kind of sharp, and it's really fascinating to read. Oh, Georgia.
Poetic.
Yeah.
Thank you very much for this inspiring presentation. I would like to say something, emphasize something about the history of the reception of Euclid, that it's kind of a common knowledge that is, like, after Bible, the most printed and circulated and read book in the history of Western culture, which is very refreshing and fills us with optimism that reason somehow actually has its charm.
Yes.
It is another thing fascinating for me is the fact that the Arabs actually first in the 9th century translated it, and the first Latin translation came not directly from the Greek but from the Arabic. And very later on then they had a direct translation. And until the 19th century, where it was very intensively criticized by Russell and co, his approach, which is interesting as well. He was dominant, obviously, in the mathematical world and in our understanding. I would like to ask, if I may, the following. How do you think his writing, in terms of style, in terms of, obviously, because it's the first systematic approach of presenting geometry and others, not only about geometry, but mainly, let's say, geometry, this first systematic approach and presentation of mathematical material, how do you think his style and language and approach and his didactic ways kind of perhaps not democratized, but popularized science, the knowledge? And thank you very much.
Yeah, thanks, Georgia. That's a great question. And by the way, I've tried to read Euclid in Arabic, but my Arabic needs a lot of work. Because Arabic, they don't write the vowels, so that makes it harder for someone like me that doesn't know his Arabic. But yes, that's a good question. I think Euclid's style is very plain. He uses a tiny bit of syntactic creativity, but it's usually for emphasis. He's not showy. He's trying to be, and so I like the way that you say he wants to be available to anyone to read. So you saw the Greek that we looked at. There's nothing fancy, right? There's nothing super rhetorical. It's just like, here's the facts. Here's what I want to do. Here's my drawing, and then here's me proving that I did it right, and here's what I did. And so I think I haven't thought much about Euclid's style being deliberately, are you suggesting trying to make himself as available as possible for everyone? But I suspect that makes sense. He's not trying to write mysterious, confusing, cryptic, super sophisticated style. He's using, once he's defined his terms, he goes back and he keeps using the same terms over and over again. He almost gets, he does get very repetitive, as to you're going to do something, you've done it. Let me just tell you again, this is what I said I was going to do, and I did it. So everything is crystal clear and not open to ambiguity or confusion. So that's a partial answer to your question, but I like the question. I should think about it some more. But is that helpful?
Thank you. I mean, if you compare it, because you mentioned Tim Myers, of course, it's another genre, but still, it's two worlds.
Yeah.
Thank you so much. Yeah.
No, you're welcome, Georgia. That's great. And the Timaeus, I look at a bit of that in my class too. And of course, Plato and is talking about according to probability, the Earth, the cube should stand for Earth because that's the most reasonable. And you can, as you say, it's a different genre, a different style, and it's a dialogue. Well, not so much dialogue in the Timaeus, but yeah, thank you very much for the question. Yeah.
May I comment on that? This is Carl.
Yeah.
Just to jump forward 1,500 years, it's worth pointing out that Kepler tried to build his model of the solar system, a heliocentric model of the solar system around the Platonic solids, using that as he thought that the Platonic solids would give him the spacing of the orbits of the planets. But actually, I actually wanted to comment in relation to George's question. It's interesting to think about at the point in the history of science where Euclid actually becomes an obstacle to understanding. And I'm thinking particularly of Newton, because Newton had to develop, the calculus to give his theory of physics and of gravity and explain the planets. But he wrote the Principia, as in the style of Euclid, as geometric propositions, which was completely unsuited for the types of mathematics that he had developed. But the model of Euclid was so strong, he felt compelled to take the calculus, the type of mathematics that he had developed, and translate it back into a geometric language, and then present it in the style of Euclid, which made it much harder to understand.
Thank you, Carl. I've read some Newton in Latin with some of my Latin students, and it's not Virgil, that's for sure. But yeah, I appreciate that. That's really interesting. And the Kepler, I think I wasn't aware about the Platonic solids as part of Kepler's system. So that's because, of course, Kepler took Copernicus from the circular orbits into the elliptical orbits. And doesn't legend have it, he got some inspiration from a container of beer or something like that? And that's probably a legend.
I haven't heard that one.
This is great. I really appreciate that. Jack.
Yeah. Graeme, yes. I want to thank you for putting in the history there with the Proclus and his pointing out that Euclid picked up on and systematized prior mathematics, Theaetetus and
Eudoxus.
Theodorus.
Yeah.
And he Proclus says he was Platonic. Well, but looking at the nomenclature, I'm more reminded of Aristotle's Analytics. Protasis, Apodoxis, Symperisma. That's those are building blocks of the syllogism.
Kind of sort of going with George's question too, kind of a more of an Aristotelian style. I like that. Let me just add one thing. I just read a review of a new book on history of Greek math by an Israeli guy, Reviel Netz. I think I'm going to buy it too. I got 2 books I need to buy. And he just wrote a 500-page book, not supplanting Sir Thomas Heath, but kind of looking at it from a different angle. So that's something I'm going to look at. Okay, Keith, I think we need to wrap it up.
Yeah, time to wrap it up. Thanks Graeme, so much for this amazing presentation of something kind of new for our group. And thanks to you all for the questions.
Yeah, thank you.
Hope to see you all the next open house.
Thanks, guys. Good to see you all.